Hi, good afternoon, everyone. Thanks for taking the time to attend this SMaRC seminar. Today, I'll be talking about my PhD project and what I've been doing the last 1 year and what I'm going to do for the next few months. It's on hydrobatics controlling underactuated underwater vehicles. So first, I'll talk about this challenge called underactuation. I'll talk a bit more on the technical side of it and also on why it's relevant to underwater robots. And then I'll talk about some ways to address this challenge, starting with linear and hybrid control, and then also with optimal control and model predictive control. And putting all of this together, I'll talk about moving forward, how we're applying this to real world scenarios, what other strategies and augmentations we can use to address this challenge, and also other collaborations and spin-offs while solving this challenge. So this is a slide that most of you would have seen once before, but just to recapitulate, what is hydrobatics? Hydrobatics refers to the agile maneuvering in underwater vehicles. So there are two broad categories of AUV designs. On one side, you consider these flight style vehicles, which are underactuated, which means they're optimized for efficiency and speed. They're designed to go far and fast. And on the other side, you have these ROV kind of vehicles, which are designed to be more maneuverable and precise in their motions and not really designed to go far. Uh, if we can get these flight style vehicles to be a bit more agile and to be able to maneuver in more tight environments and be more precise in their maneuvering, then we could be able to extend this performance capability of flight style vehicles to be from this blue spider chart to this red spider chart. And if we have that, we can make AUVs that are both efficient and agile in principle. So this could be like a new way to design robots, and we could think of new applications. So this is the motivation behind the kind of research we're doing. And uh, in order to address this and to explore this further, a big challenge is the challenge of underactuation. So an AUV is a dynamic system which can be represented by a second order ordinary differential equation. Uh, in that equation, x double dot equal to f1 plus f2. The function f1 of x dot t refers to the dynamics of the system that's only influenced by the state of the system x. And the other function f2 of x dot t times u is also influenced by the control. So this is the active dynamics that you can control with a certain control input in the actuators. So such a system is fully actuated if the rank of this f2 function is the same as the dimension of the state vector x. This means that we have as many independent controls as we have degrees of freedom. So, and we can influence each degree of freedom with one specific control. The same system can be underactuated if the rank of this f2 function is less than the dimension of x. This means that we don't have independent controls for every degree of freedom. And if we consider these ROVs, usually they're either fully actuated or in some cases even over-actuated. While for something like SAM or one of our torpedo-shaped robots, they're usually under-actuated, quite heavily under-actuated as well. So a key challenge is to find elegant ways to exploit this dynamics in the F1 function, the passive dynamics, uh, and to use minimum controls in F2 to achieve elegant motions instead of using brute force to make it converge to a certain trajectory. So to solve this problem is quite difficult. And one analogy to this can be like in these Kung Fu movies where Bruce Lee uses these nunchucks. Uh, the nunchuck is a very agile device. It does a lot of crazy motions. But to control it, he only uses his arms a little bit. He moves his hands a bit and he moves his fingers a little bit, and he can make it do really crazy things. So we kind of want to do that with an AUV, and that's where we're going. So in order to test these strategies and to investigate it further, we have SAM, which is an underactuated hydrobatic AUV. Um, Most of us have spent some time with SAM or seen it. Uh, so SAM is, on one side, it's slender, it is agile, and it's also designed to have a lot of actuators which we can exploit. Um, on one, we have a movable battery pack, which allows us to change its center of gravity position. We have a thrust vectoring system, which allows us to steer. We have dual propellers, which allows us to propel the vehicle while still controlling the roll angle. We also have rotating counterweights called the transversal center of gravity system to help us roll statically. A variable buoyancy system allows us to control the depth without moving on the other degrees of freedom. So with all of these controls, we also have the Jetson computer, which allows us to have quite good onboard processing as well. So the combination of these gives a very interesting platform in order to test underactuation and also to try out new interesting control strategies. If we look at the different ways we can influence the system, if we have the X motion, we can use the propellers to move, but we could also use the propellers in order to roll the vehicle. If we use a thrust vectoring system, we can influence 4 degrees of freedom. If we use the transversal center of gravity, we can only influence one. So with these, you can see that not all the degrees of freedom can be independently influenced, but we can still influence the degrees of freedom in some way or the other. So in order to actually exploit these different actuators and to perform really interesting maneuvers and controls, uh, we want to be able to play with this dynamics and couplings within the system. Uh, the first and the most simple way to do this is to consider cascaded linear controllers, where you have a bunch of PID controllers, but we have them cascaded with each other. So I will go a bit more into that in the next slides. Uh, or we can look at the dynamics of the system, like I mentioned in the previous slides. Um, then we can frame the control problem as an optimization problem and try to optimize for a certain objective. And if we do this periodically, we can also go to model predictive control. And if you're looking into safety and specific discrete actions that the robot does, then we look into hybrid systems. And if we consider disturbances, then we also might want the system to be adaptive and robust. Uh, and moving forward, I've not yet started working on this, but it's in my plans. Reinforcement learning, where we use machine learning tools to learn policies, optimal policies for control, is another interesting area. So starting first with linear control of hybrid systems. Last year, we were working a lot with Sam, and we went to ASCO to do some demonstrations. And the system that we had working at ASCO in the end is a hybrid system, and the control strategies that we developed were linear. So I'm going to talk a bit more on how that works now. So the AUV SAM is a hybrid system when we consider the control. We have the behavior tree that performs the decision making on board. It switches between discrete actions. So a hybrid system, in this case, is defined as on one side, you have discrete time, discrete actions, like from the behavior tree. And also you have very specific continuous time elements in that system. This can include specific actions, like if you want to go to a waypoint, or if you want to hold a certain depth, or you want to explore a region. Each of these actions can be in continuous time, but each action is discrete in itself and you switch between them. So among these actions, we used PID controllers. So to go to a waypoint, we had a specific PID controller to control the yaw angle. We had another controller just to control the depth. We even cascaded these controllers together. So if we want to control the depth while moving, we could first control the pitch angle to get a certain pitch, and then we regulate the depth based on the pitch angle. So in this way, you get this coupling between the pitch and the depth, but not actually using the model of the system. So it's possible to use these linear controllers and this really interesting behavior tree in order to get some robust control. Uh, and we can also address some model couplings and nonlinearities by doing this. Another thing that we can do with these linear systems is gain scheduling. So if you have a relatively complex system, you can split it up into smaller, simpler systems and keep updating the parameters of the simpler controllers so that you can get it to run in a more nonlinear environment. However, doing both of these is not always optimal or stabilizing. So you could, if you're not careful, you could end up causing your system to go very far away from where you want it to go. Also, the constraints for the actuators as well as in system are not considered. Uh, it's normally considering that it's got infinite amount of uh, operating space in most of these systems. So if we want to exploit these properties of the control system, then we look into slightly more advanced methods as well. Uh, but before that, I want to talk about the field test that we did at ASCO, because using behavior trees and PID controllers, we can get really powerful performance already. Last year in June, we dropped the Mini Cooper under the water at ASCO. Thank you, MMT, for that. And then we had a waypoint mission with Sam. We performed like a spiral shaped search pattern, as you can see here. Uh, and at the end of it, we used the cameras on Sam to find the Mini Cooper. And when it found it, we gave the location of the Mini Cooper. So this vision worked completely with PID controls and behavior trees. and it used dead reckoning for localization. We performed a simulation to rehearse the scenario. So we used the mission plan in Neptune. We planned like a spiral search pattern, as you can see in the figure, and we followed this trajectory using SAM, and we tested this out in the simulation environment in the Stonefish simulator. Many of you are familiar with the simulation environment, but in case you aren't, Stonefish is an open source underwater world in which we can simulate specific environments and also dynamics of the AUV to a reasonable degree of fidelity. Um, the results from our mission at ASCO was that the behavior tree was having the highest priority to check for emergencies, and if there's an emergency, come to the surface. If it's not an emergency and if it detects the scar, it will perform, it will return success in the mission. And if that's not the case, it will continue doing what it was doing, which is to follow the waypoints. So those were the actions that it did. And while we followed the mission, you can see here that within the limits of the dynamics of the system, it was trying its best to follow the waypoint that was provided. This is what I meant that using linear controllers, it allows you to perform the mission. It follows the trajectory quite well, but we also have some limitations that uh, by using just a PID controller, we cannot know that the AUV is not capable of going all the way in this mission, for example. Uh, so in the end, what happened was we got reasonably good results using linear controllers and the behavior tree, but we also were motivated to try out more advanced controllers to do these really tight maneuvers, which are a little more complicated. Here are some videos of how it looks like when we're doing the mission. So I'm going to share another screen now, just for that. Just a moment, please. Okay, can you now see my screen with pitch and buoyancy control?
Yes.
Okay, perfect. So, so here is one example of what we are able to do with the actuators on SAM with really simple linear controllers. We're able to use the actuators to push it down to 90 degrees of pitch, for example. And I'm going to skip forward a little bit to show you some heading control. We can also make it move straight by following a specific heading, or even to hold a position. Like if we try to push it to stay at zero velocity, it will try to come back and hold its position, for example. And if I tell you about our mission at ASCO, when we're doing that mission at ASCO, here it's following that spiral search pattern. Here you can see that Sam is trying its best to turn and go in a spiral. So all the controllers are working in tandem. It's getting feedback from the DVL and GPS. Uh, and the behavior tree is running, checking for emergencies. And if something happens, it aborts or performs emergency actions. So it's relatively, what do you call? In this case, we are only controlling the depth and the heading using the propellers and the thrust vectoring system. And we're not really using the trim actuators during the mission. We're using the buoyancy system for emergencies. So in this way, we're not exploiting the full capabilities of all the actuators, but we're being safe and trying to do something simple in that sense. And And now I think the AUV has stopped because it's actually found an emergency because it went too close to that rock, and that's why it stopped and aborted the mission for that time being. And another thing that we can do is pitch and depth control, like I mentioned before. So here, right now, we're using the variable buoyancy system as well as the longitudinal center of gravity subsystem to hold like a certain depth. I think it's like 2 or 3 meters depth, and to pitch up and down to plus minus 45 degrees. And it does it reasonably well. And this is using only PID controllers, which is what I mentioned before, that we're using linear control on these hybrid system of AUV. Let me go back to my presentation now. Just a moment, please. Okay, now back to my presentation. Now we are there. So we've seen both the positives and the limitations of using classical methods. So of where does PID and work well and where it doesn't, in that sense that there are some limits to the maneuvering and the capabilities. And now I will show you what we can do with more advanced techniques like optimal control and model predictive control. So, like I mentioned in the beginning, while I was describing the problem of underactuation, exploiting the dynamics of the system can help us generate quite elegant controls. So if we formulate this control problem as an optimization problem and formulate a control objective, like to follow a certain trajectory or to minimize energy consumption, for example, and to use a dynamics model and provide specific constraints, we can solve this optimization problem using existing techniques, either using dynamic programming or Pontryagin's minimum principle, or nonlinear programming or other numerical techniques in convex optimization. And the solution of this optimization problem is the optimal control. Um, this gives us the best possible result in terms of control, but there's also a catch for that. Like we can get a really nice and elegant control strategy, but whether we can solve this problem in real time while the robot is in motion is a different question. Uh, in order to make it more feasible in real time, and also to make it a little more robust to disturbances, we could think of applying this optimization with a receding horizon strategy. So this is something like playing a game of chess, where if you're playing chess, when you're playing against your opponent, you think forward for up to 4 or 5 different moves, but you only apply one move in the next step, and your opponent does the same. So if we do the same thing with control, we could find this optimal solution for the next 10 seconds and apply the control only for 1 second. And in the next time step, we again compute for the next 10 seconds and apply the 1 second. So in this way, we can first have a shorter horizon. So we can only compute for the next 10 seconds instead of for the next 2 minutes, because we know that we're going to recompute later again. And the second thing is, while we're computing that solution, if we have some disturbance, and between now and the next time we compute, if we have some disturbances and our situation and our state changes, we can still find a solution that accounts for this disturbance. So we get increased robustness and possibly increased speed with this shorter horizon. So when we do this, we get model predictive control, and you can see that in the figure here. So if you have a predicted state, which we propagate the system to, maybe up to a prediction horizon of n, and then if we have certain controls in the green line that is being computed for every time step, we only apply the red circle, and then we again recompute at k plus 1, and then do the same thing again. So this process can continue over and over again in model predictive control. So if you want to apply this to SAM, these are the different aspects of the system. So if we consider the AUV system here, in the beginning, just like I showed before, if you have a mission plan and they have a behavior tree that performs supervisory control, it tells the rest of the control system what action is needed to be done. When the supervisory controller provides an action, and from the system, when we get the estimated state, a motion planner can provide certain control objectives to say, like, follow this trajectory with minimum time, or follow this trajectory with maximum following of the trajectory, and also provide certain constraints to use or not use some actuators, or to have a maximum speed or a maximum depth, for example. And putting this control objective and the constraint, the MPC will provide actuator commands to the system. And at a more advanced stage, if we have some interesting system identification strategies, we could then update the prediction model in the controller. So these are different aspects of the system. The dynamics of the system are right now are used as the full nonlinear dynamics. We have the kinematics and the dynamics as Fosen's 6 degree of freedom robot model. So the first equation refers to the kinematics of the robot, which is the velocities versus the positions. And then the second is the dynamics, which is accelerations versus the velocities, which is like a virtual spring mass damper system there. As an objective, in this case, we're looking at following a reference trajectory, that's eta ref, and we're trying our best to follow it while using as little control as possible. So the second and the third term minimizes how much control we're using and how fast the control is changing. So we want to have as steady and as small a control as possible to follow a reference trajectory. That's the problem we're trying to solve. And in order to solve it, we can use sequential quadratic programming, which is a pretty interesting solver in MATLAB. And we could also use convex optimization or other techniques. So right now I have implemented it in MATLAB and I have also implemented it in Python. The testing is going in both. And I've got good results in MATLAB. I'm still working on the results in Python. So I'm going to talk about the MATLAB results now. One limitation that is very important when we're doing all of these kind of model-based control strategies is that the prediction model is very important. Whatever optimal control you get is only as good as the model that we use. If you consider a system like SAM, which is hydrobatic, it's very nonlinear. So in a linear system, the CL graph is just going to be a straight line. But now here we have this curve in 3 dimensions, and the same for the drag coefficient. So depending on which region of the dynamics that we are at, depending on what velocity and what orientation we are on, our dynamics are very different. And if we don't consider the linearization only at that point, we will not have a very valid model. And therefore, we have to be very careful in what model we're using when we're doing these kind of controls. So when I was using nonlinear model predictive control, it was implemented in MATLAB. The main aim was to validate the method offline. So it might not work in real time, but to see if the controls that are generated are actually making sense. So we tried maneuvers of increasing complexity. We started with maybe going quite simply to a waypoint, like maybe just going straight, or maybe making a slight turn, and then trying to turn in a very tight neighborhood, and then also to hover and to hold like a very hard orientation. And finally, to perform something like a inspection in a helix. And doing all of these things, I could find the general 3D trajectory tracking is possible using this technique. So if this is the algorithm that was used, so we consider for a certain prediction horizon, we keep computing the control. So we consider a reference trajectory, we gain state feedback, and we compute this model predictive controller based on the reference trajectory and the feedback. And it keeps applying the controller at each time step. So it's quite a simple algorithm to do it, but the solver itself was in MATLAB. So the simplest case, just to go to a waypoint, so starting from 0, going to maybe 6-meter depth, here it just goes straight up. And if you consider the controls from the nonlinear solver, you get like, it maxes out the RPM and then goes down back to minimum RPM just to stop. And then once it stops, it trims to get into position. And that's what you can see in this picture. So this looks quite reasonable. Intuitively, I would come to the same answer just as the optimal control did. If you want to do this turbo turn sequence, so if you want to turn with a very tight turning radius, here the turning radius that I want to turn and it's only like 1 meter. I provided a goal point at 90 degrees and maybe 1 meter away of 90 degrees orientation. And what the control, what the MPC suggested was for the AUV to do this turbo turn sequence where it goes maximum RPM and then minimum RPM plus minus. So it kind of turns on the spot. And this was the same kind of maneuver that Ivan and I had come up with without this optimization, and the optimal controller came up with the same solution. So we could get this turbo turn sequence using MPC. If it had to hover at 90 degrees to kind of, from where it's standing to go up and stay at 90 degrees hovering, we could use this turbo turn sequence again just to hold its position and then use the trim actuators to trim it to 90 degrees. And this as well used a different combination of actuators. So you could use the propellers and the trim at different stages. And this controller was able to exploit those couplings. And finally, if we want to really push the limits to do this kind of helix maneuver, when we want to turn in a very tight space and also point the AUV in a specific way to take a look at certain object, for example, then here you can see that we could use the propellers and the thrust vectoring to maneuver the vehicle in a certain way. And we use the trim actuators, which are also going between max and minimum values to position the sensor suite, for example, to a certain angle. By doing all of this, we could find like in all of these cases, we see that the control goes between maximum and minimum values. And we call this bang-bang control. And in the field of optimal control, in many cases for these kind of systems, the bang control is the optimum. And it's normally very efficient to do that because then you don't change the control much. You just apply a force and then you stop applying the force and then it's supposed to just reach that set point. Um, Generalizing this whole problem to go to any 3D trajectory point, if I could specify a point with a position and an orientation, the AUV would start, it would transit there, and it could also use a trim to go to that specific orientation. So this is more like a general thing that the AUV would do during a mission, and it seems to work quite well with this solver and with this optimizer. The only catch, however, is that it does not work in real time. It takes around 10 times as far. If I want to simulate a maneuver that lasts 15 seconds, it takes me 1 minute to simulate that with the solution. So you can't really apply it in real time, but there should be ways to make it run in real time. So one thing that I'm doing now is doing this time varying model predictive control. So I'm finding, instead of the nonlinear system, I'm linearizing the system because computing the solution for a linear system is much faster than a nonlinear system. So I'm linearizing the system at every time instant, piecewise, and then finding the linear control for that time instant, and then again recomputing it in the next instant. So it's kind of what you're doing is taking this nonlinear system and getting a piecewise linear system instead from that. So the algorithm then is that we define a resolution at how fine we want to linearize it. Uh, and then we compute the linear MPC at every time step. And after certain steps, we also linearize again and again so that we don't deviate so much from the nonlinear model. So this was verified in MATLAB. And now I'm also implementing the same thing in ROS using CVX. And I also want to try the Ocado solver to do the same. You can see that linearizing has its positives and negatives. You lose a little bit in optimality because you don't get the full nonlinear system and you're not solving for the full nonlinear system. But on the other side, you gain in speed. Uh, like I said before, this is the same maneuver that I had 2 slides ago, the going to a random 3D point. So this was a control from the nonlinear MPC. When I linearize it, you get broadly very similar behavior. It's not exactly the same, but it's similar. But you can also see these jumps in the middle, which is because I'm linearizing at every 2 seconds. And then you can see these jumps whenever it's being linearized. Uh, the overall policy is the same. It uses the thrusters to transit to that point and then uses the trim systems to adjust once it reaches the point. But the way it's implemented is, it can lead to problems unless we linearize it in a good way. So putting all of these together, now what I'm looking at is on applying this to new scenarios on the actual hardware, and also on augmentations, and how this can be used for collaborations as well. So the first thing I'm considering is on algae farms. We're all working together on the demos in June, and we want to perform also a model predictive control in these algae farms. And then another scenario where these kind of controllers could be useful is for calving glaciers, where you could also have a lot of obstacles. You might have to react very quickly to disturbances. You might have to do more hard maneuvers. So these are 2 areas where we think there might be utility. So I'm going to talk a little bit more on the algae farm scenario here. So a scenario with Sam. And this picture here, thank you, Liling, for this picture. Uh, we want to maneuver Sam through an algae farm. So in the picture here, you see like 2 lines, and in the simulation, some algae for, growing from these lines underwater. And we want to maybe maneuver through the algae farm and to follow these lines of algae with visual and sonar input. I think for the simpler transits, we will use PID controllers, just like we did at ASCO. But for more advanced maneuvers, like turning around or maybe inspecting something, we're going to use the MPC. So for this, I'm implementing a real-time MPC in ROS, and I'm going to test these strategies in the Stonefish simulator before deploying it in the real world. So this week, the SAM team had been to Kristineberg, and this is how the algae farm looks like in real life right now. In order to augment the MPC that I showed you before, I said that disturbances and uncertainty are a big issue, because if you have a disturbance, maybe the solution you compute is not accurate. So here, feedback motion planning and having funnels of uncertainty as a constraint or as part of the objective can be useful to improve the robustness of the system. There are techniques such as control barrier functions, which Ozer is a good expert on, which can help improve the safety of the system. Using data-driven methods, such as deep learning, can be used for system identification. So we can update the prediction model in the model predictive controller. This can allow us to do more adaptive control, or if we can do this also online, we could have dual control as well in the future. And reinforcement learning, like I said before, where we can learn from these field data and simulation to get these optimal policies from machine learning. Taking all of these together, there are also some collaborations that I've been working on right now, which are on one side related work, and one side it's an extension or an augmentation of what I'm doing. Um, First is what Ariel already mentioned, these energy management strategies with Hugin and Lolo. So I've spoken right now for the last few minutes on underactuated systems. If you're considering a hybrid powertrain, like in Lolo or in what we want to have, the fuel cell and a battery, it's an overactuated system where you have two inputs and one output. And then we want to optimize this in real time. So it's also an optimal control problem, and we could use these strategies there. So we're doing that with Clemens and Ariel. And the other thing is for manipulation. So if you see this little animation here, uh, we want to add a gripper on the nose of Sam, and using these really tight maneuvering techniques to aim Sam at an object and maybe grip it. So there are two master thesis students, Shariklia and Somnath, who are working on this. Shariklia will work more on the control and the gripping part of things, and Somnath will work more on the localization and object tracking with visual odometry. And when I was talking about this adaptive control and system identification, I'm collaborating with Chris here, and we're supervising a master thesis by Badi from ECS, who's working on using Lagrangian neural networks to learn a model of an AUV which looks like sand. So these are all the things that have been happening so far. So right now I have some exciting results with MATLAB and MPC, and I'm now working really hard on getting that to run with Python and ROS and on the actual hardware. So I'm open to all the questions you have now. Thanks for listening.